genes that select for adaptations to actually having a body that has those adaptations. And we're going to start with a cartoon. Gary Larson is one of my favorite cartoonists. He's the author of the Far Side strip. And you guys are, probably way too young. And even if you were familiar with American comics, this one I'm going to show you panel by panel. So we open on a product called Stop It, which we're being shown it can be used to stop a leaky faucet. And then we can see a woman using Stop It to stop a taxi. And a man using Stop It to stop his wife from smoking. We can see a family stopping their baby from crying. We can see someone on safari stopping a charging elephant. And we end on the money shot. Stop It, an all-purpose product. Would anyone like to share with the class why this seemingly simple series of images and that information about what Stop It can do makes this a joke? Sure.
Hi, I believe it's that this thing is not actually useful in the real world. People just using it literally by what is said on this label says "stop it," but figuratively it doesn't work at all in the real world. That's
Yeah,
why
exactly right. Exactly right. That there's no such thing as something that could do each and every single one of these things, at least effectively, right? At least in the way that you want it to, without producing all of the side effects that you wouldn't want it to. So this is going to be an analogous comic strip, but here's the version of that joke for psychology. And most people are not going to find this one as funny or think of it as quite so ridiculous, because our intuition about how the brain works isn't exactly the same as how our intuitions about physical tools, physical objects work. And that's something that we should think about, because maybe our intuition is wrong. What this kind of fundamentally boils down to is a debate that's been going on in psychology and kind of the philosophy of science for a long time. It's the debate between what's called domain generality and domain specificity. We're going to get into a little bit more of a sophisticated and specific and nuanced definition of what these terms mean. But for now, if you don't already have a sense of what they mean to most scientists, let me fill in some details to give you some placeholders to start out with. When psychologists think about the brain being domain general, what they mean is that it has a small number of mechanisms, and that those mechanisms are not specific to any particular kind of thing in the world. And the reason why we can use that small number of mechanisms that are applied generally is because they start out with relatively little built-in knowledge, but over the course of experience, this is the definition of what empiricism means in this context, that based on the evidence that you get as that mechanism, you come to learn lots of things. And throughout that learning, you're able to do a lot more specific things. But you started out with just a few general mechanisms that didn't have any of that built-in specificity beforehand. In contrast, on a domain-specific view, we're typically assuming that the brain contains many mechanisms. And these mechanisms are different from each other because they apply in different domains of thing in the world. And because of these different mechanisms having all of this different specificity, this is contrasted with the empiricism with the notion of nativism. And nativism can mean lots of things across contexts, but in psychology, the word nativist means that specificity is built into the brain as implicit knowledge. That's part of the reliable development of the brain that you don't need to learn in the way that people think about learning. Rather, it's this built-in specificity that allows us to learn all the things that we learn. If we step outside the field of psychology for a minute, imagine if I asked a carpenter whether her tools were domain general or domain specific, right? Thinking back to that physical world. If you open up a toolbox, you'd see a collection of different tools for different purposes, right? You'd see a wrench for applying torque. So you wouldn't be able to necessarily apply as much pressure with your fingers as you could with a wrench. But you couldn't cut metal with it, right? You would need something like tin snips for cutting metal. And you couldn't cut through a thick tree with that tin snip. You would need something like a saw, right? And you couldn't hammer nails with a saw. That's why you would need a hammer. The tool business is a multi-billion-dollar-a-year market with many, many, many different kinds of tools. Just considering the hand tool market, that's $6 billion a year in the US. If there was a single tool that could be designed to do all of the jobs that a carpenter needed to do, the inventor of that tool would be one of the richest people on the planet, right? And so the fact that even in 2022, when we have all of the amazing things that we do, the fact that we don't have a multi-purpose tool like that should show us something. It hasn't happened and it won't happen because there's no such thing as a domain general carpenter's tool. But domain general theories have been popular in psychology for almost the entire existence of psychology, or at the very least for more than 70 years. The most classic group of domain general theories in psychology is the behaviorist tradition. On this view, the brain has only a few basic mechanisms, a few basic innate mechanisms, born-in mechanisms, like classical and operant conditioning, or a few types of reinforcement learning, plus a few built-in motivators of behavior called reinforcers and punishers, and that's it. Everything that a 5-year-old or a 10-year-old or an adult can do, everything they know that a baby doesn't, is due to histories of this kind of experience or conditioning, learning from the environment. That it starts with a very simple stimulation that has consequences, and that because of those consequences, you change. And it's that history of changes over time that takes you from being a baby to being an adult who can do all of the things that an adult can do and knowing all the things that an adult can know. So you can see that this is a kind of classic example of a domain general theory, starting off with just a couple mechanisms, applying those mechanisms to almost everything, and starting out with basically no information in the system and learning everything through experience. When the cognitive revolution came to psychology in the 1970s and 1980s, psychologists didn't really give up the domain generality of their theory, even though they replaced it with a more updated version of information processing. Some of the most popular and long-standing models of how the brain works are as an association network or a neural network, where simple rules of reinforcement learning tune the weights between those general processing units. The idea here is still that there's some input that takes stimulus, and then some kind of computer that, based on all of the connections between nodes in the computer, they can get trained to do anything. And then an output layer that puts out behavior on the basis of that computation. This theory is still a domain general theory because the idea is that anything can serve as input, it can learn anything, and generate any behavior on the basis of that learning. Starts off with a simple mechanism, just that kind of mechanism, and by virtue of its interactions in the world, it builds up knowledge. Domain general. The hallmark of a domain general theory is the assumption of equipotentiality. That's a big word. The idea, though, is very simple. Equi is equal, that first part, and potential is like able to. It simply means the equal potential or equal ability of all possibilities. The possibilities here are the connections or links between stimulus and behavior, the possible tunings of a neural network. Equipotentiality says that it's equally easy to condition any combination of stimulus and response, equally easy to tune an association network to do one thing or another. So I want to ask, why do we recognize that that product, stop it, is impossible? But thinking about the brain as a domain general tool seems appealing. Why do we recognize that the carpenter's tools have to be domain specific, but we keep holding on to our domain general theories of how the mind is? In other words, why is domain generality a seductive idea? Here are at least a few likely reasons. If domain generality is true, it's a pretty parsimonious solution. Parsimonious means that it can explain things without having a very complicated structure. And if you think about the idea of Occam's razor, which is often the phrase that's used to summarize parsimony, the argument is that of all of the available explanations, the simplest one is the most likely to be true. But that's only if all of the explanations are equally good at explaining the data. And so that's going to be a question we need to think about. Why does this seem to be parsimonious, though? It promises to explain everything that humans think and do, and it does so with just a few simple mechanisms. The developmental view that we get from domain generality is that it fits the pattern of development, right? If you look at a baby, it seems like they don't know much and they can't do much. And it takes a long time before they're an adult where they can do the things that adults do and know the things that adults know. And it also fits our instinct blindness, right? We feel like a unified self. We feel like there's one of us. We don't feel like a collection of thousands or hundreds of thousands of mechanisms. When we learn how to ride a bike or learn a new song or study for a test, we feel like it's us, like in me. I feel like I'm the one who's doing it. You feel like you're the one who's doing it, who's doing that learning. It doesn't feel like there are different parts of ourselves that are learning different things in different ways. But going back to that example of vision that we started the course with, that should give us reason to be suspicious of these intuitions. When we considered the example of vision, we concluded that what feels simple and easy is often only simple and easy because it's enabled by an underlying set of complex machinery. But we can't simply rely on our suspicions, of course. We need data to inform us, right? We want to be compelled to our beliefs on the basis of data. And that actually started to pile up very quickly. And actually, I'm going to redo this share. 1 second. Bear with me for a second, because I need to share my sound. Okay. The data that psychology was likely not going to be domain general started to show up right around the time that behaviorism was taking off. Harry Harlow was a psychologist working in the middle of the last century. And if you've taken a psych course, you probably have already heard of him. At this time in world history, we had just come through World War II, and millions of families had been disrupted by the deaths of parents, and there were many children that were left in the care of strangers and orphanages. Harlow was interested in figuring out how those children could learn to form attachments to a mother object, and what kinds of changes to the environment, what kind of learning experiences might make that work better, right? How could we get children to form a better attachment, even if their family life was disrupted because of the war? As a behaviorist, the first tool that he reached for was the theory that attachment behavior was conditioned by food. This is the domain general explanation, that what we have is a built-in reinforcer. Even from birth, we find food to be reinforcing, rewarding. And that because mothers tend to feed you, that's why we associate good things and we associate being close to our mother. If this theory is correct, we should find that when a creature has an experience of food provisioning, being fed by something, that should be all that's required for an infant to form attachment with a caregiver. And this theory says that there's no other built-in or innate details of what a mother is expected to be. So Harlow decided to test these predictions. In his experiments, he obviously didn't use humans because that would not be ethical. But at least at the time, he considered it ethical to do these experiments with monkeys, rhesus macaques. So he raised rhesus macaques from birth in the presence of two potential caregivers. Both of them were constructed out of chicken wire, and they both had a little spot where a bottle could be hung. What he calls the wire mother is simply that. It's that wire cage without really any mother-like features. The cloth mother, that's the name for the one on the right, is basically that same apparatus, but it has fur on the front, and it has a more realistic face. It has the configuration of a face that you would see if you were this kind of creature, if you were a rhesus macaque. Each of the mothers had a spot where the bottle could be placed, and so this is how the experiment worked. Half of the baby monkeys were raised in a cage with both of these mothers, where the bottle was put on the wire mother. And so they experienced a history of only being fed by the wire mother. And the other half of the monkeys, raised in that same setup, had the bottle placed on the cloth mother. So they only experienced an association with the bottle being on the cloth mother. And so the prediction is that whatever it means to have an attachment to your mother, we should see that that's tied to whichever is the model that fed the monkey. That there shouldn't be any difference between those two conditions, because on the domain general view, the only thing that's built in is a mechanism for classical or operant conditioning, association, essentially, and that built-in food reinforcer. Let's see what happened.
Let me show you a monkey raised on a nursing wire mother. Now here are 106's two mothers. As you can see, it was weaned on a wire mother. Here's baby 106. Watch.
He's going to the wire mother.
It's got to eat to live.
Oh, he's going back.
He's back on the cloth mother, and he'll stay on the cloth mother. Actually, this baby spends from 17 to 18 hours a day on the cloth mother and less than 1 hour a day on the wire mother. We had predicted that the variable of contact comfort would be a variable of measurable importance, but we were unprepared to find that it completely overwhelmed and overshadowed all other variables, including those of nursing.
Frankly, Doctor, if it comes to a choice between wire and cloth, it's reasonable to expect that any child will go to the cloth. It's a matter of creature comfort, like a baby with its blanket. But is this really love?
Well, what do you mean by saying that a baby loves its mother? Certainly one thing we mean is that it gets a great feeling of security in the presence of the mother. Now, Mr. Collingwood, wouldn't you say that if you frightened a baby, that it went running to its mother, was comforted, and then all the fear disappeared and was replaced by a complete sense of security that that baby loved its mother? Now, in this experiment, this is the apparatus we use.
That looks diabolical.
That's just the way the baby monkey feels about it. Flashing eyes, loud sounds, moving mechanical parts, all of these things are designed to frighten a monkey. Now here we have a peaceful, resting baby monkey. Let's find out what his reactions to his mother are when we frighten him.
He's scared, all right.
And he does what any child will do in a similar situation.
He runs away.
It's more than running away. He was running to his mother, to touch her, to drive away his fear. Contact with the mother changes his entire personality. Look, now he's actually threatening the diabolical object. All right. This gives us part of the picture of the strength of infantile love. This is a 6-foot square room with a few toys and other objects. But to the monkey, it's much more menacing. We know that when our own children are taken to a strange place without their mothers, they are often overwhelmed with fear. This room is just such a new and strange environment for the baby monkeys. No mother is in there. Now, let's put a monkey into the room. Notice how cautiously he enters the room. He's searching for comfort, but nothing relieves his disturbance. Now we'll take the baby monkey out and put in a wire mother.
Now, this one was nursed by a wire mother.
That's right, all his life.
She doesn't seem to help much.
Now, we'll try the same test with a cloth mother in the room. You see the contrast in the behavior? Despite the fact that the wire mother nursed him, she could offer this infant nothing in the way of affection or security. But here the monkey, by rubbing against the cloth mother, as if he were seeking as much contact comfort as he could get, builds up his reservoir of affection and security. First, his body relaxes as the fear disappears. But above and beyond this, new positive response patterns appear. He now goes out to explore and investigate this new, strange world. He is now a normal, happy, curious baby.
All right. So under the equipotentiality assumption, those results shouldn't have happened, right? Equipotentiality means that all reinforcers, all stimuli, all behavior should be equally easy to associate, equally easy to learn. They would suggest that something that is built into human nature, that is built into an animal's nature, that is so specific as a mother concept shouldn't exist. But these results suggest that there actually is a preferential relationship. There is information built in. Rather than having nothing built in, like a concept of furry, that mothers are supposed to have that softness, that mothers are supposed to have those faces, despite the fact that these infants were only being reinforced by food from the wire mother, every single one of them uniformly sought comfort from the cloth mother. They only had those they only had those reactions of having their anxiety go away, of feeling safe and secure so that they could challenge a situation or go on to learn new things, when they were with that mother who didn't feed them, that mother who simply had the features that matched a template for mother, that if equipotentiality was true, shouldn't have been built into the system. So these data violate the idea of equipotentiality and suggest that a domain general view is wrong. But that wasn't enough. A few years later, some more evidence came from Marion and Keller Breland, who were the star students of B.F. Skinner. B.F. Skinner was the founder of behaviorism in the United States. His first book that kind of published the idea of behaviorism, The Behavior of Organisms. After graduating from Skinner's lab at Harvard, the Brelands took their expertise in animal training and founded themselves a new tradition that they took into the private sector. In the late 1950s, they were hired by an advertising company to do some animal training for a bank commercial. Now, I don't know why the people at the ad agency thought this would make a good ad, but what the people in the ad agency wanted them to do was to train raccoons to put coins into a piggy bank. And I guess the idea was that this was showing the idea of saving, maybe. The Brelands said, no problem, we're behaviorists, we know how to do that. If you want to get an animal to do a complicated behavior, like picking up a coin and walking it over to a piggy bank and dropping it in, then all you have to do is design a shaping protocol using food as a reinforcer to reinforce closer and closer and closer approximations of that ultimate desired behavior. So they did that, but it turns out they were wrong. They couldn't train the raccoons to do that behavior by using a food reinforcer. They couldn't get the animal to do that. They wouldn't put the coins in the piggy bank, despite all of the food that they were getting for getting closer and closer and closer to doing that. Instead, the raccoons produced a behavior that they were never rewarded for. They washed the coins in their water dish. Why did they do that? Well, in the natural environment of raccoons, they are scavengers. They collect food that's often dirty. And a behavior that they do in the wild is wash off food in a river or stream before eating it. Under equipotentiality, that shouldn't have happened. They should have been able to condition any behavior using a food reward. There shouldn't be a specialized connection between a reinforcer and a behavior that's already built into the system. So if you start off with a baby raccoon that has never lived in the wild, you shouldn't have this behavior showing up. Yet despite these raccoons never being rewarded for putting coins in their water dish, that's exactly what they did. This is a pretty big violation of equipotentiality. In fact, it was such a violation of the fundamental domain general principles of behaviorism that it motivated the Brelands to publish these data. And B.F. Skinner, who was at that time the most famous and dominant psychologist in the entire field of psychology, he had his book, The Behavior of Organisms. The Brelands, his star students, published The Misbehavior of Organisms. And they began the article with an amazing sentence. They said, "There seems to be a continuing realization by psychologists that perhaps the white rat cannot reveal everything there is to know about behavior." What this is alluding to is the experimental conditions that were present in Skinner's labs. Because it's not ethical to do tests on humans, his idea was, well, we can do all of our experiments with animals like rats or pigeons, because anything we learn about how they learn should be exactly generalizable to humans, because not just humans are domain general learners, but all animals are domain general learners. The only difference is that they have a smaller brain, a less efficient mechanism, a weaker mechanism. We have a bigger brain, a bigger mechanism. That's his idea. But they don't have their own species-specific nature where there's built-in information. But if that's not true, right? If these different creatures have their own species-specific natures, then you can't use another creature like a white rat to learn everything you need to know about how humans behave. But these data didn't convince everyone yet, and behaviorism kept rolling along. A few years later, John Garcia achieved some of the most compelling and damning evidence against domain general equipotentiality-driven behaviorism to date. And one of the reasons why this was so compelling is that what he found was a double dissociation. A double dissociation is when you can show that not only do you see an effect go in one direction, you see the effect getting reversed so that the behavior goes in the opposite direction when you change the conditions. And what that does is it shows you that it's not simply because there's something fundamental about the difference between these two stimuli. But let me get more specific. The behavior that he was working on was conditioned taste aversions. These are those things that you learn to kind of hate to eat because of some experience that you had when you ate them in the past. Like maybe you ate it and that afterwards you were sick, or maybe you ate it and then afterwards you threw up. The idea is that these aversions that you have is just operant conditioning, using punishment as an explanation, right? Punishment reduces behavior that precedes it. And so if you experienced a punishing stimulus, a punishing reinforcer after having eaten a food, that should reduce the likelihood of you eating that food. And because operant conditioning is supposed to work equipotentially, it shouldn't matter what kind of punishment you use, right? Even though most of the time, if you think about the punishment that would follow eating a food, if it's a food that causes that kind of reaction, like throwing up, it's going to be causing a reaction like throwing up. It's not going to be causing some other punishment. It's not going to slap you across the face, causing pain. It's a bolt of lightning isn't going to strike you, right? And so while there is this kind of association in the real world, the argument is that that association doesn't already exist in the brain. So to test this, Garcia ran the following experiment. And he used rats, not because they should be a perfect model for human behavior necessarily. He was kind of testing that idea. And he was interested in seeing how wrong it was. And so what he did was he did a 2 condition by 2 condition, so a 4 condition experiment. So these were rats that were raised from birth in a lab. And he exposed them to one of 2 types of cages. There was they were all in a cage where if they went to a certain part of the cage, a light went on. And if they went to another part of the cage, that's where their water was. And the water had some saccharine flavor so that it was something that they would want to approach, but it gave it a little bit of a funny flavor. And that light is not something that they were used to. As they went to the part of the cage, there was a light that would turn on. You don't usually have lights turn on when you move to places, right? So either when the rats approached the water, a light would go on, or when they drank the water, it had this taste. So they could either avoid approaching the light or approach drinking essentially flavored water. And the question is, under what conditions do they avoid the water? Is it when the cage is electrocuted and they get a painful experience? Or is it when the water, when they taste that water, they're dosed with a little bit of radiation that makes them nauseous and they throw up? So I misspoke earlier. It's not that the light was in the part of the cage where the water was, the light was in a different part of the cage. And so it was actually when they were approaching one part of the cage, the light would go on, or they could be going to the water where the water had a taste. And so what did he find? What did the rats avoid? Under equipotentiality, having that painful experience should teach the rats, they should learn not to go in that part of the cage because that's where the hurt is, and not to drink the water because that water produces pain. Or they should also learn, for the other half of the rats, not to go in that part of the cage where they get sick, and not to drink the water that makes them sick. They should learn to avoid all of those situations. But despite, for 1/4 of the rats, experiencing shock during that water condition, and another 1/4 experiencing shock in that light condition, they didn't learn to avoid the water when it was being punished by pain. They did learn to avoid that area of the cage when it was being punished by pain. But here's where that double dissociation comes in, because you might think, well, maybe there's a certain amount of punishment that you're applying by shock. And maybe there's just an inherent amount of reward that drinking water has. And so maybe those things balance out such that you don't see that same strong response of learning in the water condition. But because going to a cage where they have other choices of where to go, maybe it's that it wasn't as inherently rewarding to go to that part of the cage. And so that same amount of punishment was strong enough to condition aversion in the light condition, but it wasn't strong enough to condition aversion in the water condition. But here's the double dissociation, because when the punishment was that dose of radiation that caused them to get sick, they didn't learn to avoid that part of the cage when it was being cued by a light. But they did learn to avoid that part of the cage when what they were drinking there was water. When the punishment was making them sick, they stopped drinking from that water source. And you can't explain this pattern on the basis of just an effect of the punishment being strong or weak, or the situation being rewarding or not, right? We have a double dissociation here. And that can only be true if you have at least two different mechanisms. So why would this be something that happens with rats? Why should a rat have a mechanism in their head that produces this kind of result? Well, we can think about how rats in their natural environment and how they evolved. They're omnivores, right? They eat lots and lots of different things. But lots of the things that they eat could be toxic, right? They could eat a new plant, and that plant could have some poison in it, and they need to learn not to eat that. When your digestive system detects a toxin, it triggers a nausea response to make you throw it up, right? To limit your exposure to the toxin. And learning from that experience to avoid eating that thing, that would be the kind of specialized association that you would predict if you thought that natural selection built in domain-specific adaptations within a species, right? Because if you ate something that wasn't so good for you and you threw up after, it would be good to avoid eating that thing in the future. This is a picture of Subway rat, but this was probably not so present on Chinese media as it was in American media when it was taken. In any case, this is the exact opposite of what you would predict from domain generality. This is a violation of the equipotentiality assumption. Because under equipotentiality, any punishment should lead to aversion, right? You should stop doing the behavior that's being punished. And there shouldn't be a preferential relationship between one kind of punishment and one behavior and a different kind of punishment and another behavior. Despite there being equal associations in the lab, the rats only paired what made them nauseous with what they ate. And they only paired electric shock with that part of the cage that had the light. Violation of equipotentiality. So we've seen some of the evidence that the mind is not fully domain general, but now let's look at some reasons why we should actually expect it to be domain specific. First, if you think about problems in the world, those problems that the brain might have evolved to solve, just like the different problems that a carpenter faces are domain specific, the problems in the world that behavior is designed to solve, those are domain specific. For example, problems can have really different solutions, right? If the thing that you're trying to do is find something to eat, and your choices are an ice cream cone, Idris Elba, and an Indian rhino, the thing that you should be judging on is like, well, what has the highest sugar concentration? What tastes the best, right? Ice cream cone. If you're trying to pick a good partner to mate with, you should be judging not on how sweet they taste or how much sugar they have in them, but cues of attractiveness, right? Cues of health. And if you're thinking about which should you stay away from, you shouldn't be using what's the sweetest or what looks like it's the healthiest, but you should be using cues of danger, right? The thing that has a big sharp horn that's very, very heavy, such that if it charges at you, it would kill you. That's the thing that you should avoid, right? So finding a solution to a problem is not a domain general solution because success in each of those domains is different. When you found something to eat, it tastes good. When you found something to mate with, you can have a baby. When you find something to avoid and you avoid it, you don't die, right? Different indicators of success. A domain general choice mechanism can't solve all of these problems at once, right? Because by being associated with, like, being rewarded for doing a behavior, it can't pick out what the nature of the problem is, right? It can't learn to approach and avoid the same thing. A second reason to expect natural selection to have actually selected domain-specific mechanisms is that domain-specific tools just work better than domain-general ones. Think about a butcher knife. You might not be a fancy chef who cooks with a butcher knife, but you can probably at least imagine that a butcher knife is very flexible, right? You can cut many things with it in your kitchen. Like, you can chop up vegetables, you can slice through pieces of meat, you can cut through bones, right? But if you were going in for surgery, you wouldn't want your surgeon to use a butcher knife, right? You'd rather that your surgeon uses a scalpel. It's a better tool for the job, right? The point here is that domain general tools lose ability. They lose utility in different specific kinds of problems whenever the solution to the problem is in conflict, right? Where the best size of tool, the way that you hold the handle and how heavy it is and the size of the edge, when that best set of conditions for butchering meat is not the same set of conditions that makes it best for surgery. Like, for doing surgery, you need a precision grip. You want it to have a much smaller edge so that you can get in and do detail work, right? You can't be both big and small. You can't both be hold like this and hold like this, right? You can't have both of those perfect solutions. The best you could do is have a partial solution, something that was in between, something that did both of them a little bit okay, right? So that domain general tool would solve butchering worse than a butcher knife would, and it would solve surgery worse than a scalpel. So if you were only limited to having one knife, it would be better to have that more domain general knife, because at least you could solve both of those problems a little bit. But there's no reason to think that you can only have one mechanism. It's only because we're committed to domain, that idea of domain generality, that commits us to having a small number of mechanisms, right? Because if you can have more than one knife, that would be better, right? You could have a whole toolbox of tools. It's kind of why in the real world, a contractor has a whole toolbox. They don't have one magic tool. This is Doctor Who's sonic screwdriver. There's a reason why the sonic screwdriver is fiction, and it's kind of magical whenever you see Doctor Who use it to solve a problem, and the doctor doesn't have to run around with a whole toolbox. It's also why, like, Batman, who doesn't have any special powers, has to have a whole utility belt, where the magic alien, Superman, doesn't need to have a utility belt, right? The magic alien can do magic. But in the real world, if you were just a human, you would need a utility belt with all those tools. Third, for domain generality to work, it requires you to actually have that experience of learning, and usually more than one experience, because you actually have to build up that history of reinforcement or punishment to learn to approach or avoid something. But there are some problems that you just don't have time to learn that way. There's some problems that if you don't avoid it, even before you experience the resulting punishment, you're just dead, right? Imagine if you had to learn which of these animals to avoid on the basis of operant conditioning, right? If you didn't avoid the predator, you would just be dead. Or learning whether volcanoes are dangerous to jump into. How do you learn not to jump into a volcano? You can't learn that through trial and error, right? Or whether or not this mushroom is safe to eat. Don't eat those, by the way. That's a death cap mushroom and it'll kill you. You can't learn any of these by trial and error. On the other hand, if natural selection over a long period of time where mutations that cause those effects, that mutations that cause an aversion to certain kinds of things in the world, when those mutations appear, natural selection would spread them in a species because they produce positive effects. Natural selection can essentially learn that over evolutionary time, such that all of the members of a species have that built-in knowledge in them, but it's a domain-specific knowledge. Finally, the appeal of domain generality largely involves how it can apparently learn anything. But is that because we don't understand how complicated learning is? Because when you get down to it, learning really requires domain specificity. If you've encountered what's called the Gavagai problem, if you've taken a philosophy class, you already have this idea in mind, but I like to think of this, and it's also called the frame problem in psychology. I'm going to use another Gary Larson cartoon because I think he gets it quite aptly. If you can't read the caption because you're too far from the screen, the caption is, and this is what the teacher is saying, yes, I think there's a question at the back. Why is this a joke? Why is this funny? It's funny because when we see that the lesson is a picture of a cow and the word cow, it seems obvious what the lesson is, right? He's saying that that's a cow. How could you have a question? But how do you know what is actually being taught? How do you know that what's being labeled there is like not just that drawing? It's not just that those lines on a page are the cow lines, right? It's your intuition is that that's a kind of cow. If you saw more of those in the real world, those would all be cows. But think of all the things that you could infer if you weren't able to assume that that was the one thing that was being labeled, right? Because you have the exact same information that, yes, it could be that what's being labeled is that category, though that is one cow and there's more than one cow in the world, that whole species are cows. But it could be that what the teacher is teaching you is that that's the name of that one individual, like Fred or Bob or Joe. This is cow. None of the other things that look like that are cow. They have their own names, right? That's equally consistent with the evidence that you have. It's also equally consistent to think about that it's not that the whole thing is cow, it's that those horns, what we would call horns, that those are cow. Or it might be the color, that maybe that's cow color. Or maybe it's the state of mind that's being represented there. It's a cow state of mind, right? If you don't have a constraint on what you think is being taught, what you think it is that it is to be learned, you can't learn anything because there's literally an infinite number of theories that are all consistent with the data that you have. This so far is what's been described as that frame problem or the Gavagai problem. In the Gavagai problem, it's very similar. The idea is that imagine yourself as an explorer on an alien planet, and you walk up to an alien, because there's aliens, and the alien points to what looks to you like a plant, and it says the word Gavagai. How do you know what just happened? How do you know what gavagai is? How do you know if it's the plant, if it's the direction, if it's a part of the plant, if it's the color? You can't make an inference about what the alien was labeling for you. You can't learn words. You can't learn what words are for. This is a fundamental problem with word learning, because that's the only kind of experience we can get, right? We only can get labeling events. We can't get something that would discriminate between one particular meaning of a word and all of the infinite possible theories of what that word could mean. So we need built-in structure in our head that allows us to focus in on a particular theory of what's happening so that we can very quickly learn what words mean. But the problem is actually more complicated than even that. Like, so far, it's an infinitely hard problem, but it's actually a multiply infinitely hard problem, or you can call it the frame squared problem. Because how do you know that what's happening is an act of labeling, right? How do you know that what the teacher is doing is telling you that whatever he's saying this is, whatever the this is, that it's a cow, right? Sure, it could be the category or the individual or the part or the color or the state of mind, right? That's being a cow label, but it could be a command, right? It could be a, when you see this thing, cow it, right? It could be an instruction to do a verb on that thing. How do you tell the difference? Or could it be something else entirely that it's hard to even imagine, because with my human mind, my mind is focused in on a finite set of possibilities. This is evidence that our brains contain these domain-specific mechanisms because it requires them to actually accomplish learning. So for these reasons, we can say that domain general mechanisms, mechanisms that truly come with no built-in specificity, simply don't work and are therefore very unlikely to be the product of natural selection, right? Because if they don't work, and if there was a mutation that caused them, that mutation wouldn't spread by natural selection, because it wouldn't actually produce those positive effects, because the domain general mechanism doesn't actually solve problems in the real world. But that doesn't mean that we have a definition of domain specificity that works yet. We should think about what kinds of domain specific mechanisms, what kind of mechanisms do we expect to be a result of natural selection? Going back to Mars' computational level of analysis, we can think about mechanisms being specific in at least two ways. First, there has to be specificity in terms of the content. What are they picking out of in the world? What are they applying to? For instance, is a mechanism about avoiding dangerous predators, in which case it has to pick out animals and have cues of which animal is dangerous in order to know to avoid them? Or is it picking out food, in which case it should be using different cues? Or is it about picking mates, in which case it should be using different cues, right? So it needs to be knowing what's the kind of thing that it should be applying to in the real world. And we can also think about specificity in terms of the function that's being accomplished on that content, right? What's the designed outcome? So what do you do on that information such that you then do the behavior that is supposed to happen? How do you process that information? Let me give you some concrete examples. Consider this hammer. We can define both its content and function specificity. The hammer wasn't made to be used on everything in the world, right? Because the size of the head, the length of the shaft, This hammer was designed to work on small objects, rigid objects like nails or staples. It doesn't work on things like water or sand, right? Hammers don't work by using them in any random way, right? Like you couldn't nail something by using a hammer, like tossing it to the side or letting it sit on a table, right? The hammer only works when you use it in a specific way, right? Only if you do a specific function with it. The hammer works by taking your muscle strength, and by virtue of the shaft being longer, it increases the momentum of the swing. And because of the weight of the head is being concentrated into a striking surface, that magnifies and concentrates the force that you're able to apply. That's the reason. All of that specificity is the reason why only a hammer that has certain characteristics can actually, by doing that function, succeed at solving a problem when it's applied to certain things, like hammers and nails. Staples and nails. Seen this way, we can all agree that a hammer is a domain-specific tool for hammering things like nails. But you could also use it for other things. Like just because we can see it as domain specific doesn't mean that you couldn't smash a window or smash a smartphone or use it as a bookmark or go on a murder spree, right? This is just scratching the surface of all of the things you could do with a hammer. Does that mean that a hammer is not domain specific? We need a few more concepts to help us out of this dilemma. When we think about domain specificity, we need to separate the proper domain of the mechanism from the actual domain of the mechanism. The proper domain is the full scope of content and function that the mechanism was designed to operate within. For a human-made tool like a hammer, we can say that this was what the tool was made for. This is why it has the features it has. And this is why there's such a tight relation between its form and its function. In this case, the proper domain includes things like nails and staples and the function of, hammering, right? In contrast, the actual domain is all of the content and functions that it can do, like applying to a book by weighing it down and applying to a window by smashing it. If you think about a mechanism designed by natural selection, the proper domain of the mechanism is that structural regularity in the adaptive problem that caused a mutation that produced that effect for being selected by natural selection. That's why the mechanism has the features it has, and why there's that special relationship between the adaptive problem and the adaptation that solves it. The actual domain of a natural mechanism is, given that the adaptation is built in a certain way, given that it has a certain algorithmic solution and a certain implementation, what are all the byproduct uses that it has? In other words, we can tie the proper domain of an evolved adaptation to the computational level description of the mechanism, and we can tie the actual domain to the implementation of that mechanism. Let's see how we can use these concepts on a new example, this coin sorter. I had something like this growing up, and I loved it. My dad would always come home with pockets full of change, and my sister and I got to dump the coins in and watch them get sorted into denominations, and the total counted up. The problem was my dad was a contractor. He was a building contractor. And so he always had a bunch of other things in his pockets, like washers. And to our never-ending frustration, the washers would also get sorted because some of them were like quarter-sized, and they would throw off the money total that was being displayed on the screen. We didn't have as much money as we thought based on what the screen said. So what can we say about the coin sorter? Is it domain specific or domain general? It certainly processes coins. It categorizes them by size. It counts up the different kinds and it totals up their dollar value. But it also processes washers and does those same things to the washers. So it seems to be applying generally. But once we separate the proper from the actual domain, we can see that it is actually domain specific, right? The proper domain is coins. The actual domain includes small coin-sized objects. But this isn't just a difference in the word definitions. Think about how the proper domain is useful and the actual domain is not, right? Because which of these domains explains why the machine has the features that it has? Why is a particular size of coin-sized object associated with a particular dollar value? Why does a particular size of coin-sized object fit through that slot? Why don't bigger things fit through the slot? All of the features of the coin sorter are tied to the proper domain of the mechanism. And it's simply because, well, given that arrangement, some other things are going to be available as a byproduct, like washers fitting in. That's going to be available within the actual domain. But that actual domain isn't what caused the mechanism to be designed that way. The engineer wasn't thinking, oh, we should put washers in it because we should make it so that washers can fit. That's not the reason why it has the design. The reason why it has the design is that quarters are a certain size and dimes are a certain size and nickels are a certain size. Another example that comes from psychology is the idea of the fusiform face area. This is a chunk of brain tissue located near what's called the fusiform gyrus, and it's been identified in both the left and right hemisphere. And the area got the name fusiform face area because many studies have found that it's activated more when people are seeing faces than pretty much seeing any other thing. And when that region gets damaged, you get a disorder called prosopagnosia, where you can't recognize people's faces anymore. And that region is also activated when you're trying to process whether a face is displaying an emotion. But other things make it in, right? Kind of famously, there was an experiment where subjects were trained to be able to categorize these different shapes. They were called greebles. And after someone became an expert in knowing which one was a foop and which one was a deep, now showing them a greeble, you see a activation in their fusiform face area. And you also can, look at the grille of a car where there's those two headlights and, a bumper, and you get activation in the fusiform face area. But we can see that that is just the actual domain of the mechanism because those things have face-like configurations. It's a domain-specific mechanism for processing faces. And we can see that once we separate the proper domain from the actual domain. Look at all of that cluster of design features. The mechanism is really good at rapidly telling the difference between different people. It recognizes people's faces, and it does so using the information on the face that it sees, and it can use that information to give a cue of emotion. This is evidence that it's a domain-specific mechanism for processing faces, as long as we understand it in terms of its proper domain. Looking at the remaining evidence, the evidence that other face-like objects are also processed, and that when people get a lot of experience processing those objects, it processes them in the fusiform face area. That shows us that it's part of the actual domain. But which one of these is responsible for natural selection designing it that way? Obviously, it's the proper domain. The proper domain is faces. Sure, we can understand its implementation. We can say that face-like things actually make it in, but Which domain is responsible for the design of the mechanism? The proper domain. So at this point, we can say that we have an updated view of human nature in light of this new information. We can predict that human nature is a collection of adaptations that we have now because they solved an ancestral adaptive problem. That's how natural selection works. These adaptations should be species typical, with an underlying computational architecture that's universal to humans. This is the implication of sexual reproduction. On top of that universal human nature, we expect there to be individual differences in one of a few different ways: facultative calibration, pathogen-driven mutation selection balance, byproduct uses, etc. These species-typical adaptations should now be domain-specific. When we define domain specificity as applying a constrained set of processes to a limited set of content, such that a computational adaptive problem can be solved. That computational problem is the proper domain of the mechanism. But since all mechanisms have to be built in a specific way, the specific way that any mechanism is built is going to result in an actual domain that operates over a wider variety of content as simply a byproduct of however that mechanism is built. So let's go back to our idea of what genes do. What are they for? What's actually getting selected by natural selection? We've said that genes are for adaptations, but the problem that we're going to think about, that problem of how you go from a baby to an adult, is that the adaptation doesn't show up as that adult form, right? The adaptation shows up first as that first stage, right? It's like a building doesn't show up right away. You have to go from a blueprint. And that blueprint tells you the process of how you build a building. So we should be thinking about genes in the same way. We should be thinking about genes as for adaptation development. They can't simply encode the adult stage. And so when we think about that development, that's going to tell us a few new things that are going to change the kinds of adaptations we expect. You could think of this set of ideas as similar to that phylogenetic step constraint, where over evolutionary time, the mutations that got selected had to go through a series of functional adaptive steps. The same thing applies to development over the lifespan. You can't build a building in any particular way, right? You couldn't start from the roof and work down. You would have to start from the basement and work up, right? Because if you started from the roof wouldn't stand on its own. So you have to build the building in a way using a process that goes through a series of functional steps. We should think about the same thing when we're thinking about human development. For example, why is it that an embryo has certain characteristics and not others? Why does it have an amniotic sac? Why does it have an umbilical cord? And why does it have a primitive heart? Well, if you didn't have an amniotic sac, you couldn't keep your resources, right? If you didn't have an umbilical cord, you couldn't get those resources from mom. And if you didn't have a heart, you couldn't circulate those resources around your tissue so that you could grow. If you didn't have those problems solved, if you had 3 different features as your first features, development couldn't keep going forward. That is, some adaptations are going to emerge early, not because they're simple and easy to learn, but because they're the necessary ones for the organism to develop first. This is just a reiteration of that idea. So this gives us a reason why we need to think about the stages of natural selection as targets of natural selection themselves, like teeth. Why don't babies have teeth? Is it because you have to learn how to have teeth and you have to go through an approximation of steps? No, it's because humans are mammals that nurse, and teeth get in the way of nursing. And if we look at all mammals, we see that they have this juvenile face that's good for nursing that changes into an adult style face that would be less good for nursing. You eliminate those really strong cheek muscles. It's why babies have those really strong cheek muscles and older kids don't, because babies have to spend so much of their time sucking. If you tried sucking on a straw for 16 hours a day, you wouldn't be able to do it, but babies reliably can. It's because they have adaptations that you lack. So this gives us another way of thinking about adaptation as needing to have a life history perspective. There's nothing specific about adulthood that is the target of where natural selection should operate. We can see this in the example of the lancet liver fluke. This is a really crazy creature with a really crazy life history. The way this fluke works is that it's a little flatworm. When it's an adult, it has sexual reproduction with other flukes and it lays eggs. But in order to have those eggs spread and get out of that belly of that sheep, because if you were just in the belly of that sheep and that sheep died, that's the end of you. You need to actually get into the bellies of other sheep. And so the eggs get excreted with the sheep poop. Sheep don't eat each other's poop, so that's not a way that you can get back into the belly of other sheep. But it turns out that snails do. And so the eggs are designed to be excreted in such a way that snails would pick them up as they're consuming resources from poop. And when the fluke eggs are in the belly of the snail, they go through a developmental stage where they start becoming multicellular little encapsulated cysts. And those end up getting excreted. They get passed out of the snail in the snail's slime. But sheep don't eat snail slime, so that creature hasn't solved its full life cycle adaptive problem yet. But ants eat snail slime. And so now that you're these little encrusted balls of cells, you've ended up in the body of an ant. But sheep don't eat ants yet. What this mechanism does, what this little creature does, is amazing at this point. It goes through a little bit of a mutation where it attaches itself to the ant's neurons. It's ganglion. It's not a full brain. And it basically turns the ant into a zombie. It makes the ant do something that ants don't normally do. It makes the ant crawl up a blade of grass and clamp its jaws on and stay there for the rest of its life. That's not normal ant behavior, right? At that point, a sheep coming by eating the grass will end up eating that ant. And that's how the lancet liver fluke gets all the way back into the belly of another sheep. Thinking about that life history, we can't characterize those steps, right, as a sequence of steps that a creature would have to go through just on the basis of learning, right? We don't go through a stage where we have to zombify ants on the way to our adulthood, because that's not one of the adaptive problems that our species faces. But it is an adaptive problem that another species faces, and that's why it's part of its species typical design. I think that I'm not going to have time to do, okay, let's see here. Let me condense this. I'm going to skip this bit. If we look at humans, we can see that while we don't have that crazy life history like that Lancet liver fluke does, we do have a series of stages in our life where we have to do different things. We have an infancy period where we basically need to grow. We have a childhood period where we need to learn, right? We need to learn social skills, etc. We have an adult period where we need to be productive and reproduce. This is the lifespan of humans on the bottom and 3 related species: chimpanzees, gibbons, and macaques. Those are monkeys. The middle 2 are apes like us. What's mapped out in those horizontal lines is the period of life where females can have babies, where they can reproduce. The interesting thing, if you compare macaques, gibbons, and chimpanzees, is that all of those stages, the prenatal period, the infant period, the juvenile period, the adult period, the female reproductive period, they're all proportional to each other, such that it was like you took a rubber band and just stretched it or shrank it, because everything is expanding and contracting in the same ratio. But humans have a different life history. That the human is not what you would get if you simply stretched out a chimpanzee. We have a much longer juvenile period than you would expect if we were simply an older chimpanzee, a chimpanzee that lived longer. We delay the start of female reproduction, but it ends at essentially the same place. We then have that huge portion of life after reproduction. How does this make sense? Well, comparing humans to chimps, where chimps have, on average, in the wild, 1 baby every 6 to 7 years, humans, under natural conditions, without access to birth control, in pre-modern societies, have a baby every, on average, 3 years. In other words, in the female reproductive time span of the same length, humans are able to squeeze twice as many babies in compared to chimpanzees. How? Well, we're able to do this long period of learning so that we can be better at acquiring resources, so that we can have more resources available during that reproductive period. And we have that huge period of late life where we can be producing such that we can still be taking care of babies that need to spend those, 18, 20, 22 years. How many of you are still dependent on your parents? Taking care of our kids, even if they're born at the end of our reproductive time span, right? And that we can still be producing to invest in our kids and our grandkids. That's how we pay for that time in our development. All right, I am going to stop there and take a break for questions. So just to remind you, today, we've covered why there's no sense in thinking about the brain as a domain general device. All of the reasons why domain generality doesn't work and domain specificity does. And then those developmental pieces. Yes, there's a hand raised.
Hi, so basically you mentioned different types of creatures and they have certain characteristics when they grow up, like the raccoons. A raccoon that had never been in the wild, and that raccoon somehow learns to watch the food. And then we have this liver fluke that basically paralyzes ants to allow them to stay on grass So sheep eat them, and then they stay in the livers of the sheep. So basically, different creatures have to go through certain characteristics, and these characteristics are domain specific. And different species have different these kinds of characteristics. Is that right?
Yes, that's right.
Okay. And then you mentioned this phase area, right? It recognizes phases, and it's activated when it recognizes phases. What if this phase is upside down? We cannot recognize this phase anymore.
Yeah, that's right. If you think about any mechanism, in order to solve a problem, it has to have specific features. That's what allows it to solve a problem. But by solving a problem doesn't mean that it can solve any version of that problem. Like, think about your calculator. Your calculator has a built-in memory such that it's able to operate over numbers that are within a certain range. If you've ever done like a activity on your calculator where you like times 2 times 2 times 2 times 2 times 2 times 2, and you keep going, eventually you get to a number that the calculator can't compute over. It gives you an error. Any mechanism, in order to solve some problem, has to have specific features. Those are what enables it to solve that problem. But based on the features that it has, it's not going to be able to solve every version of that problem. But the versions of the problem that it can solve are the ones that it's been likely to encounter. And that's why it has those features that solve that problem. And it can't see the future, right? It can't see all of the potential problems it will solve. That's why it doesn't have features that only are in problems from the future. So like the face area. The face area is for recognizing faces. And most of the time when you're encountering a person, they're right side up. Though we don't live in a world where people are walking on the ceiling. And so we don't encounter upside down faces as part of the natural world. If we went into space where, you know, there was no gravity and any surface could be a walkable surface if you wanted it to be, maybe we would start encountering upside down faces, and maybe it would be good if we had a mechanism that could do that, but we don't. And the reason we don't is because that's not part of the natural history of selection for a face processing mechanism. The natural history includes all of those experiences that were in the past. It doesn't include any of the experiences that are in the future.
Right, so the upside down faces are not in the proper domain. They're in the actual domain.
They're sort of in the actual domain because we can't, like, applying our face recognition to upside down faces doesn't really work that well.
Okay, well, thank you so much for answering my question. The lectures have been really fantastic.
Thank you. I think we might have time for one more. All right. Well, thank you for that compliment. I hope everyone has found this to be good. We're going to be having next a test on these first 4 modules of material. This is a midterm exam, 30-question multiple choice. I'm going to make sure that that midterm only includes content that I was able to get to in these lectures. If you've printed out the slides, you'll see that there are some slides that I wasn't able to get to. There won't be any questions on that material, so you don't have to worry about trying to guess what I was going to say for that material. You can just consider what we talked about during class. All right, I'll see you in 2 weeks. Good luck, everyone.